Right now, NASA is quietly funding a plan so audacious it sounds like science fiction. A plan to turn our own sun into a telescope. Not a bigger telescope, not a fancier satellite. The actual sun turned into a lens $40 billion in the making, capable of photographing a planet trillions of kilometers away in enough detail to make out oceans, continents, and possibly even city lights. Einstein himself looked at this idea and basically said, "Forget it, this will never happen." But scientists at NASA have spent years quietly proving him wrong. And they think it could happen within your lifetime. Before we get into exactly how, hit like and subscribe. It genuinely helps this channel keep making videos like this one. Now let's talk about the problem that started all of this. We've found thousands of planets orbiting other stars. Thousands, and here's the strange part. Almost every single one of them is basically invisible to us. We know their size, we know their mass, sometimes we even know their temperature, but visually, they're just numbers on a spreadsheet, inferred from a tiny flicker of starlight or a barely detectable wobble. We have never actually seen one. Not really, not with continents, not with weather, not with anything moving on the surface. So why not just build a bigger telescope and look? Well, here's the problem. Even our most powerful space telescope right now, the one with a mirror over 6 meters wide, would need a mirror roughly 90 kilometers across just to resolve any real detail on a planet that far away. That's not a slightly bigger telescope. That's a mirror the size of a small country. And even if we somehow built something that large, we'd run straight into a second, nastier problem. The star these planets orbit is blindingly, catastrophically bright compared to the planet itself. An Earth-sized world can be 10 billion times fainter than the star it circles. Picture trying to photograph a firefly hovering directly in front of a stadium floodlight from hundreds of kilometers away. That's the actual scale of the challenge. Scientists call it the contrast problem, and for decades it's been the wall nobody could climb over. So a small group of researchers asked a different question. What if we stopped trying to out-engineer the universe and instead just used something it already gave us for free? To understand what they came up with, we have to go back over a century to a man almost nobody has heard of. In 1915, Einstein published General Relativity, describing gravity not as some invisible pulling force, but as a warping of space itself. Massive objects bend the fabric around them, and light bends right along with it. 20 years later, a struggling immigrant named Rudy Mandel, working odd jobs in Washington, D.C., with zero formal scientific training, had a striking realization sitting in his head. If gravity bends light, then a massive object like a star could act like a lens, bending and magnifying the light of something far behind it. Mandel was so sure of this that he actually traveled to Princeton and somehow got a meeting with Einstein himself. And Einstein wasn't impressed. He figured the effect would be essentially unobservable and not worth the paper it was written on. But Mandel kept pushing, and eventually, kind of reluctantly, Einstein wrote up the idea and sent it off for publication. In private, Einstein reportedly grumbled that he was only doing this to make the poor guy happy, and that the whole thing had little real scientific value. He even closed the paper by saying there was no real hope of ever observing this directly. He was wrong. Decades after Einstein's death, astronomers started spotting exactly this phenomenon out in deep space. Distant galaxies warped into glowing arcs and rings by the gravity of massive objects sitting between us and them. These are called Einstein rings, and today they're a completely normal tool in modern astronomy. Then in 1979, a scientist named von Eschleman pushed the idea somewhere nobody had gone before. He proposed that we could deliberately use our own sun as a gravitational lens. Not to study faraway galaxies, but to focus in on one very specific, very deliberate target, an exoplanet. So here's the actual physics, and stay with me, because this part is wild. Light traveling from a distant planet passes near our sun, and gets bent slightly by the sun's gravity. Because the sun is a sphere, light passing on any side of it bends by roughly the same amount, and all of those bent rays eventually meet back up again along a single straight line stretching out from the sun. That line of convergence starts around 550 times the distance between the Earth and the sun, and it just keeps going, essentially forever. If you put a telescope anywhere along that line and look back toward the sun, you won't just see a bright star sitting there. You'll see the sun surrounded by a glowing ring of light. And hidden inside that ring is the light of the planet you're targeting, magnified by a factor of roughly 100 billion. That's the same effect as building that 90-kilometer telescope, except the sun builds it for you, completely free. And this is the part that makes it so elegant. This approach completely sidesteps the contrast problem, because you're no longer trying to block out an overwhelmingly bright host star. You're focused entirely on the planet's own light, gathered and concentrated by the sun's gravity. This concept now has a name: the Solar Gravitational Lens Telescope, or SGLT for short. But of course, there's a massive catch. 550 times the Earth-Sun distance is almost unbelievably far. Voyager 1, the most distant human-made object ever launched, has traveled about 170 of those units since 1977. Nearly 50 years of travel, and it's still only about a third of the way there. We'd need to go more than 3 times farther than that, and doing it at the pace of a normal rocket would take well over a century. Nobody wants to fund a mission that won't finish until long after everyone who built it is gone. So the team behind this concept set a real, deliberate target. Get this telescope operational within about 25 years. Something a working scientist could actually live to see. Getting there that fast requires a strategy that honestly sounds a little reckless. Solar sails. Sunlight has no mass, but it does carry momentum, and when it bounces off a reflective surface, it gives that surface a tiny push. String enough of those pushes together, and you can accelerate a spacecraft to genuinely extraordinary speeds, using light the way a sailboat uses wind. To pull this off, engineers plan to send a small spacecraft, weighing under 100 kilograms, on a deliberate dive straight toward the sun. As it approaches, it unfurls a set of 16 ultra-thin reflective panels, together covering an area comparable to 2.5 football fields, yet weighing only about 32 kilograms combined. The material itself is a carbon nanotube film, coated to reflect light and thinner than a strand of human hair by a factor of 70. It has to survive temperatures above 3,000 degrees Celsius as the spacecraft swings within about 15 million kilometers of the sun's surface, closer than anything humans have ever willingly sent. At that closest approach, the sails snap fully open, catching the full intensity of raw sunlight and using the sun's own gravity like a slingshot. The spacecraft rockets away from the solar system at roughly 125 kilometers per second. At that speed, it could reach the focal line in about 20 years, blowing past Voyager 1's current distance in only around 7. But here's a real, uncomfortable question. You spend 20 years and a small fortune sending a telescope out into the dark, and then it just breaks. What now? So the plan was never to send one telescope, it's to send an entire fleet. Every launch carries a batch of small satellites, each with its own specific job. Some carry mirror segments. One carries a device to block out the sun's glare. One handles communication back to Earth. One carries a nuclear power source, since sunlight becomes far too weak out there for solar panels to do anything useful. Once launched, these small spacecraft assemble themselves autonomously into a fully functioning observatory. And here's the ambitious part. The plan is to launch an entirely new cluster of these every single year, each one spaced roughly the distance between the Sun and Neptune apart from the last. The team actually calls this the String of Pearls, a chain of tiny observatories stretching from our solar system out into interstellar space. relaying data back to Earth pearl by pearl using laser communication. If one pearl fails, the mission just keeps going, and every new pearl launched benefits from newer technology than the one before it. Now here's where this whole concept turns into something that feels less like engineering and more like actual wizardry. Once a cluster of these small telescopes reaches the correct distance, they don't just point and shoot one picture. The image of the planet isn't sitting neatly inside that glowing ring. It's actually spread out across a wide patch of sky, forming something like a giant cylinder of light. The telescopes physically have to move through this region, capturing the distorted ring shape from thousands of precise positions, sometimes needing to be accurate to within a single meter. One telescope stays completely outside the target zone, just measuring the sun's raw glow, so that contamination can be digitally subtracted from the others later. Piece by piece, position by position, each captured moment becomes a single pixel of data. And then, using the well-understood mathematics of exactly how gravity distorts light, scientists can run this entire process in reverse, reconstructing the original, undistorted image of the planet from thousands upon thousands of these warped ring captures. The farther the telescope travels along the focal line, the cleaner and sharper this reconstruction becomes. Given years of continuous observation, you could actually watch the planet rotate, mapping its entire surface over time and filtering out cloud cover as you go, the same way you'd average out noise in any long-exposure photograph. So which planet do you actually point this thing at first? The shortlist includes some names you might already know. Kepler 186f, one of the first roughly Earth-sized planets ever found sitting inside a habitable zone. The TRAPPIST-1 system, remarkable because it hosts several rocky worlds in or near the habitable zone around a single small star, meaning one mission could observe multiple planets at once. And sitting right at the top of the list, our closest known potentially habitable world, Proxima Centauri b, just over 4 light-years away. Because it's so close, it would give us the sharpest image of anything on the list, potentially resolving detail down to about 1 kilometer per pixel. At that resolution, you're not looking at a colored dot anymore. You're looking at coastlines, mountain ranges, possibly entire storm systems, and if there happens to be a civilization down there, quite possibly their cities. This isn't some fringe idea cooked up in someone's garage. NASA's Innovative Advanced Concepts program, which exists specifically to fund high-risk, high-reward research like this, has already pushed the concept through 3 separate approval phases. The earlier studies confirmed the underlying physics genuinely holds up. Later phases worked out how to actually extract a usable image from that distorted ring, how to structure the swarm of small spacecraft, and how solar sails could realistically get a probe out there fast enough to matter within a human lifetime. The most recent phase, backed by $2 million in funding, produced a complete mission architecture, essentially a real working blueprint for how you'd actually build and fly this thing. And the lead researcher has since secured private funding to build and test a demonstration spacecraft to prove the solar sail technology genuinely works in space, not just on paper. As for the full mission, current estimates put the total cost around $40 billion, spread across roughly 4 decades. That number sounds enormous until you put it next to what we already spend elsewhere. It's a fraction of the cost of the International Space Station, a small fraction of what the Apollo program cost in today's money. And for context, global military spending alone runs into the billions every single day. The money required to fund humanity's first real photograph of an alien world already exists somewhere in the world. It's simply a matter of where we choose to point it. And the implications reach far beyond a single photograph. Every star in the galaxy can act as a gravitational lens in exactly the same way our sun does, which means this same physics could one day be used not just to see distant worlds, but to actually communicate with them. sending and receiving signals amplified by the gravity of entire star systems at almost no energy cost, with almost no data loss along the way. Some researchers have even floated a far wilder idea, using the supermassive black hole sitting at the center of our own galaxy as a lens powerful enough to resolve individual buildings on a planet clear on the other side of the Milky Way. The technology to actually reach that black hole doesn't exist yet, and might not for tens of thousands of years. But the underlying physics, remarkably, checks out. For now, though, the far more achievable goal is one that could genuinely happen in our lifetimes. A spacecraft launched from Earth, diving straight toward the sun, using our own star's gravity to both fling it forward and magnify what's behind it. Sent out to try and answer a question humans have been asking since the very first time we looked up at a night sky. Is there anybody out there? Einstein believed we'd never live to see this happen, and for almost a century, he was right. But the tools, the funding, and the physics have finally caught up with the question. And if this mission flies the way it's planned, the generation watching this video right now could be the one that finally gets the answer, in the form of an actual photograph of another world. Thanks for watching, and I'll see you in the next one.